Hello. Today I'll be talking about hot Jupiters, their atmospheres and interiors. I'm Jonathan Fortney. I'm a professor at University of California, Santa Cruz, and I'm the director of the Other Worlds Laboratory here in Santa Cruz. So today's talk will, on the first half or so, will be on atmospheres of hot Jupiters, and the second half will be on interior structure and evolution. And looking at the other speakers, it looks like there'll be some other talks that touch on a variety of aspects of atmospheres, clouds, and a wider range of exoplanet atmospheres. So I'll try to do my best to cover various aspects of hot Jupiters. Let's get started. So we should think about what the goals are for giant planets generally. And that's to understand their formation, evolution, interior, and atmosphere. And we study planets today, I think, for two main reasons. One is to understand how planets work, what's the physics and chemistry of planets. And the other is to understand how planets form. That's a big open question as well. And we want to do this for a wide range of objects. When you think about giant planets, which are ones that accrete hydrogen helium atmospheres, that could be a very wide range of planets, maybe things as small as 5 Earth masses up to things as large as 5,000 Earth masses. We know these things accrete a hydrogen helium envelope. So a unified view might be a lot to ask. For our talk today, focusing on hot Jupiters, we'll mostly focus on maybe a tenth of a Jupiter mass, up to 10 Jupiter masses, but that still is a factor of 100 in mass. And so it's important to think of a hierarchy of questions to be asked, given the appropriate data for both inside and outside the solar system when we're thinking about giant planets. So the context today is, of course, hot Jupiters. So let's think about planetary categories to get started. This is a pie slice diagram of Jupiter, Neptune, and the Earth. And so Jupiter serves as kind of our benchmark for understanding giant planets. So on the left, we have a pie slice of Jupiter. We know Jupiter's atmosphere is about 3 times solar. So it's enriched in metals compared to the sun. We think Saturn's about 10 times solar. And as we go down deeper within Jupiter, we quickly transition from a cold atmosphere to a hot interior. You only have to go down about 15% of the way until you're at temperatures over 6,000 degrees, pressures 2 million times higher. And then most of Jupiter is liquid metallic hydrogen, which is a sea of protons and electrons, fully ionized, mixed with neutral helium. Deep down, we think that Jupiter does have a core. Even after Juno, this is still a bit uncertain. There's pretty good evidence now that this core is not distinct, but is dredged up into the overlying hydrogen, perhaps dredged up even halfway through the planet. So the current state of the core isn't that well understood. But it seems that both Jupiter and Saturn have some sort of central condensation. If we think about Neptune, Neptune's atmosphere and Uranus is a much higher metallicity. This number is at least 50 times solar. You could sometimes see it quoted as almost 100 times solar. So the metallicity of the atmosphere of smaller giant planets goes up considerably. Most of the mass of Uranus and Neptune is actually in fluid ionic sea of molecular fragments that people call ices. And this is also convecting as well. We think all of Jupiter's interior is fully convective. We think of most of Uranus and Neptune is probably also fully convective. This is, of course, different than the Earth, of course, where we have these well-defined boundaries. For the Earth, we've had seismology, so we can pinpoint these regions much more precisely. But thinking about exoplanets, we want to compare and contrast if hot Jupiters are different than Jupiter itself in terms of its structure, in terms of other aspects of its atmospheres and interior. So there's a classic theory for understanding planets formation, and that's this Pollock et al. This is a famous paper on core accretion of giant planets. And so what we can look at here is as a function of time in millions of years, we have the accretion of solids here in black, the accretion of gas in dotted line, the solid and gas total is the dashed dots. And this is the classic theory for how we think giant planets form. You build up a core of here 5 to 20 Earth masses that starts to accrete hydrogen, and then you might or might not reach this nearly runaway phase where you're accreting more and more and more hydrogen. And so you're accreting metals to make your core, but then you're also accreting more metals as you're accreting your hydrogen and helium. So the planet formation process should leave some sort of imprint in terms of the planet's composition, in terms of the gas and the solids that are being accreted. So we'll come back to this. I just want to point out that in terms of understanding exoplanets, in terms of the data we have today before James Webb, we're kind of redoing what we did in the solar system 40 or 50 years ago. This is a plot I really like on the upper left from Gillette et al. In 1969. This is the first mid-infrared spectrum of Jupiter ever taken, from 3 to 15 microns. This is log of the flux in the y-axis. You can see absorption due to methane. You can see that Jupiter is not at all like a black body. It's extremely bright at 5 microns, orders of magnitude brighter than in other wavelengths. You could also see that methane is in emission at 8 microns. That tells us that Jupiter has a temperature inversion. And so there's a lot we can tell from this crude spectrum of Jupiter. And actually, it's actually somewhat similar to the spectrum we have of hot Jupiter HD 189733. This is from a retrieval paper by Zhang et al. We have a spectrum here from about 1 to 20 microns, the similar sort of spectrum compared to the Jupiter spectrum. It's similar sort of data. It's our first initial look at this planet. The power of exoplanets, of course, is that we have a much larger sample size. Instead of a small sample size, we have a large sample size of excellent data. So we want to try to do this again, of course. This sort of first look data, of course, also includes other sorts of data. So on the top, this is the first map of Jupiter ever made of Jupiter's 5 micron hotspots, which are mostly along the equator from 1972. This is in some ways similar to the brightness maps people have made for hot Jupiters based on thermal emission phase curves. This is the first on the bottom for HD 189733. This has been done for other planets as well over the past decade or so. And so again, we're getting our first initial look of hot Jupiters. It's very similar to our first look of Jupiter something like 50 years ago. So I want to come back to why we study planets. I think it's important. So in terms of atmospheres, to me, there's 2 important kind of forks to think about. One is we want to understand the atmospheric physics and chemistry. That's one reason to understand planetary atmospheres. And that typically involves understanding the absorption and the emission of radiation and how that interplays with the atmospheric composition of atoms and molecules and clouds. We also want to think about circulation, the advection of energy around the planet from day to night, or vertical advection of energy. So we want to understand atmospheres to understand those physical and chemical processes. We also want to understand atmospheres to connect to planetary origins. We want to think about how our findings can connect to understanding planet formation. And that can be in terms of understanding the atomic and molecular abundances. That can also be trying to connect formation location to their composition and connect that to stellar abundances as well. And so connecting to abundances is important. And I'm sure this will come up in some of the other talks you'll be seeing. But I want to point out how this might operate for hot Jupiters. On the upper left is a plot that shows the abundance compared to the sun for a bunch of different elements. So if everything was at the 1 line, your gas giant would have solar composition. So I mentioned before that Jupiter is about 3 times solar. That's this orange band here from the Galileo entry probe, which dove into Jupiter's atmosphere in 1995 and took in situ abundances. Saturn is these red dots. We think it's about 10 times solar. There has not been a Saturn entry probe, so we're a little bit handicapped in determining abundances. Uranus and Neptune has only one determination, this carbon abundance, but it seems like it's something like 80 times solar. I mentioned 50 before, but it's a large number. There's been a variety of papers thinking about how hot Jupiters in particular might have atmospheric abundances that are different or similar to Jupiter, for instance. This is a classic plot on the left by Oberg et al., pointing out that the C to O ratio of your star, which would be the dashed line here, for the sun, it's about 0.55. How that C to O ratio could differ in the disk where the planet is forming, both in terms of the gas C to O ratio and the grain or solid C to O ratio. at these condensation fronts where you freeze out water, that changes the C/O ratio in the gas by removing oxygen from the gas, depressing your C/O ratio. In the solid, sorry, enhancing your C/O ratio in the gas by freezing out the oxygen, but depressing the C/O ratio in your solids by making more oxygen there. And so it's too simple-minded to suggest that all giant planets should have enhanced C/O ratio simply because they're accreting C-rich gas. Giant planets also accrete a lot of metals, and when you accrete a lot of metals, you could potentially decrease your C/O ratio. So the final C/O ratio of your planet depends on the relative accretion of the amount of gas and the amount of solids. So this is something people are trying to do with data today. In addition, on the right, this is a plot of Z in your envelope. This is your hydrogen helium envelope metallicity as a function of planet mass. And it's a key prediction of core accretion that giant planets, since they accrete these extra metals from the nebula, should have metal-enriched atmospheres and metal-enriched envelopes compared to their parent star. We know Jupiter is about 3 times solar, Saturn's about 10. This is a prediction from a paper that I did with Christophe Mortacini a while back, suggesting there should be this inverse relationship as you go to lower and lower mass of giant planets. This metallicity should increase. And that's what we see in the solar system. We'd like to see if hot Jupiters obey that relation as well. So I want to talk about hot Jupiter atmosphere modeling in terms of the flavors of models. I think from other talks, for instance, from Hannah Wakeford, you'll hear a bit more about observations of hot Jupiters. And so I wanted to focus a bit more on how we try to understand hot Jupiter atmospheres in terms of models. And there's kind of 3 kinds of models you'll commonly come across. So the first is one-dimensional radiative convective models. Some people will also call these one-dimensional self-consistent models. And these sorts of models are the most similar to what you might see for stellar atmosphere modeling as well. In these sorts of models, you specify all the physics and chemistry, and you iterate towards a solution. And you might do this over a grid of effective temperature, gravity, cloud abundances. And if once you make a grid of a wide range of atmospheres at different temperatures, gravities, and compositions, you could then compare the resulting spectra to what you see. This is different from other forms of atmosphere models like retrieval and 3-dimensional models. In a retrieval framework, what you're doing there is doing an inverse model. And so a retrieval model does not really specify the physics and chemistry. It's a data-driven model where you try to run millions of calculations extremely quickly, or at least hundreds of thousands, and you let the data tell you what the atmospheric abundances and temperature structure need to be to fit the resulting spectra. People have actually done this with downward-facing Earth satellites for decades, but astrophysicists actually developed this very similar method. And these 2 methods have actually grown together now. And the power of the retrieval method is that it tells you what the atmosphere is truly doing, but you lack the context of why that is, which can only come from a 1-dimensional or 3-dimensional self-consistent model. So to me, the power of atmosphere modeling comes from the fact that you need to pair retrieval with some kind of 1D or 3D self-consistent model. On the far right, the 3D dynamical model is more similar to the 1-dimensional model on the far left. But here, you're not just trying to converge to a 1-dimensional average for your atmosphere, you're doing a full 3-dimensional calculation. So you use radiative transport just like you do on the far left, but you also involve hydrodynamics. And this usually is termed a GCM, a general circulation model or global circulation model. And these 3-dimensional models are of course essential. We know hot Jupiters have a hot day side and a cool night side. There's advection to the night side. So a 3-dimensional framework really is essential to get a true understanding of these atmospheres. Typically, you have to make some assumptions though. You have to make some simplifications. You probably have to simplify your radiative transfer, simplify your chemistry compared to a 1-dimensional model. So today typically not feasible to do large grids of three-dimensional models. You might do a three-dimensional model for particular planets. So today, all three flavors of models are still essential. You need one-dimensional radiative convective models to explore a large phase space of physics and chemistry. You need 1D retrieval models to tell you what the best fits are, what the atmospheres are actually doing. And you need three-dimensional models to give you a true picture of the full three-dimensional aspect of the atmosphere. And there's a lot of work today on trying to combine retrievals with three-dimensional models to assess how well a retrieval actually can retrieve the true properties of a three-dimensional atmosphere model. So we'll talk about these each in a bit more detail now. So a one-dimensional self-consistent radiative convective atmosphere model. The things you are specifying beforehand are your abundances. You would say this model is going to be 1 times solar or 10 times solar. And that specifies the amount of hydrogen, helium, carbon, nitrogen, oxygen, all those. You then might calculate the chemistry over that wide phase space. Based on those abundances, what's the chemistry expected to be, let's say from 1,000 degrees up to 3,000 degrees, and from a microbar down to a kilobar? What's our grid of chemistry space? For all of those different chemical abundances, you then need to know the opacities, the wavelength dependence, absorption, cross sections of those molecules. So on the upper right, here is a plot of the chemical abundances of a hot Jupiter like HD 209458b. These are the abundances of a wide range of molecules as a function of pressure going down deeper in the atmosphere. We expect the main oxygen and carbon bearing species are water vapor, CO, probably not a lot of methane unless you're cold, a lot of sodium and potassium. These are the neutral atomic alkali metals. Sorry. On the bottom here, this is across James Webb relevant phase space. We have the absorption cross sections of a lot of these molecules. Titanium oxide, TiO, is a very strong absorber in the optical of very cool stars. And we have good evidence now that this is found in at least a couple hot Jupiters, and it really should be there in the hottest of the hot Jupiters. Across the infrared, most of your absorption bands are going to be due to water vapor, CO, potentially methane, maybe HCN if you have photochemistry, but we think water vapor should often be the dominant opacity source. So if you're making a self-consistent model, you've specified the abundances, you have a database of your chemistry and your opacities. You have to specify the incident flux coming from the parent star. You have to specify the intrinsic energy coming out of the planet's interior. You then, at every pressure level in the model, you have to calculate whether or not that's a convective layer or not. And in the end, what you get out is a pressure temperature profile that's consistent based on the flux coming in, the flux coming out of the bottom, and the atmospheric abundances that are absorbing and emitting that energy. And what you can then generate from that self-consistent one-dimensional solution is your emission spectrum, or your transmission spectrum, or your reflection spectrum. And so one typically does this for a given model or potentially for a grid of models. So on the left, this is a classic plot you'll see from in a lot of different ways. This is pressure going down, this is temperature. These models are actually for brown dwarfs, but I chose this plot just because it shows what I'd like to show in this plot. Models are in light blue, whereas condensation of cloud species is shown in orange or gray. And so the realm of hot Jupiters is the right-hand side of this diagram over here. The hottest of the hot Jupiters might be so hot that they have no cloud species, but most hot Jupiters should fall over here where they have cloud species like corundum or these silicates, MgSiO3, MgSiO4 in the visible atmosphere, also things like iron. And these are the cloud species that we really should be seeing in these atmospheres. There's of course very good evidence for that, as you'll be hearing in another talk on clouds in exoplanet atmospheres by Hannah Wakeford. What you typically then can do from a grid of models is generate the emission spectrum. This again, as this plot is for atmospheres a bit cooler than hot Jupiters, but I think it's a nice illustrative plot. If you have a grid modeling approach of a range of effective temperatures and gravities, you can then generate spectra. One-dimensional models also allow you to make predictions for how atmospheres should change when you change the input physics and chemistry. And so an example of this is Madhusudan 2012. Madhu has suggested that the atmospheric abundances should change dramatically as you change your carbon to oxygen ratio. And we can look at, let's say, this plot in the lower left. This is for 2000 degrees, typical of some of the hot Jupiters. As you go from a CDO ratio less than 1 to a CDO ratio greater than 1, your chemistry changes significantly. At a lower CDO ratio, CO itself, carbon monoxide, takes up a lot of your oxygen, but you have oxygen left over, which goes up into making water vapor. So the typical expectation is that your atmosphere should have a lot of water vapor and CO in it. That's over here on the left. However, as you increase the CDO ratio, CO itself takes up more and more oxygen. And at a high CDO ratio, there's very little oxygen left over to make water vapor. And so on the right-hand side of this diagram, what happens is that you're still CO dominated, but then your amount of oxygen falls off by many orders of magnitude. And the things you make instead are methane, acetylene, HCN. You have, since you don't have any, you have leftover carbon as opposed to leftover oxygen, you make a lot more carbon-bearing molecules. And so a prediction, if hot Jupiters happen to have a high CDO ratio, is that you should see very little water vapor, but a lot more of these carbon-bearing species. And that's true for a cooler hot Jupiter at 1500 K, and also for something like an ultra hot Jupiter at 3000 K. The expectation is the same: a depressed water vapor abundance and an increased abundance of things like methane and HCN. And so very soon, either from ground-based high-resolution spectroscopy or from James Webb, we should be able to put that prediction to the test. I wanted to switch gears a bit to talk more about retrieval, just for a few slides, to give people a feel for how this is applied. This is a figure I got from Mike Line. We have an initial guess for the pressure temperature profile here. This particular example is for a brown dwarf, but it works the exact same way in terms of hot Jupiters. This is a movie. On the upper right here is an emission spectrum. The object's bright here at 1.3 microns, 1.6 microns. Here's the initial guess pressure temperature profile. If we let the movie roll forward, what we find is that by running tens of thousands of models or hundreds of thousands of models, we can iterate repeatedly using an MCMC to find that we can fit the spectra with a range of possible pressure temperature profiles. Each one of the pressure temperature profiles in this plot would also have an associated amount of atmospheric abundances: methane, water vapor, CO. And so the typical output then is something like this, where this is for a hot Jupiter with sort of the best available data we have today. This is for HD 209458b. We have an emission spectrum with Hubble Wide Field Camera 3 at about 1.1 to 1.7 microns, which is also the same spectrum down here. We have some Spitzer data at longer wavelengths. The retrieval yields a pressure temperature profile here. These different wavelengths probe pressures that are around 1 bar to a millibar or so. This is where we have our constraint in the pressure temperature profile. And we end up yielding abundances. We have a well-constrained water vapor abundance, which comes from this water vapor absorption band at 1.4 microns here. We have an upper limit on on methane. We have some detection of either CO or CO2 because they both absorb at 4.5 microns. And we just have upper limits on these other molecules. This is one particular example, but it gives you a flavor for what retrieval models are trying to do. They are data-driven, and based on the observations, they drive the MCMC towards a solution with confidence intervals in terms of the atmospheric abundances and the pressure temperature profile. Finally, I want to come back to these three-dimensional models I was talking of several slides ago. Here, you're combining radiative transfer with hydrodynamics in 3 dimensions. And typically, you have to make some choices in terms of what you're going to simplify. You might simplify the radiative transfer using just gray radiative transfer, or you might simplify your chemistry. A lot of the state of the art in 3-dimensional modeling today is trying to include clouds. And that might include clouds as a passive tracer, that might include clouds as a true component of the atmosphere that interacts with the radiation. One of the things I think it's important to keep in mind compared to the solar system is that if we look at Jupiter today, we can actually see its atmospheric dynamics. We can measure those wind speeds. We can see the 5-micron hotspots. Of course, for hot Jupiters, we don't have that same ability to see the dynamics. We essentially just have the spectra. We have the thermal emission spectra that we use to tell us about the atmospheric dynamics. So the dynamics have to be inferred from this time series photometry or spectroscopy. On the left, here's a plot of 4 layers of the atmosphere of HD 209-458b. This particular model up high in the atmosphere, it's red, has a temperature inversion on the day side. As you go deeper down, it gets a little bit cooler, and deepest down, it's relatively more homogenized. And one can then post-process the 3-dimensional grid to yield the emission spectrum as a function of orbital phase. This is just one particular plot. This is an example that I worked on, but lots of different groups are doing this today, where you take a 3-dimensional model, you post-process it to generate the emission spectrum or the transmission spectrum of the 3-dimensional model, and then you compare those directly to observations. So what you get from a 3-dimensional model is a true understanding of the likely atmospheric diversity. This is a plot from Vivian Parmentier looking at pressure going down deeper as a function of temperature. And we can see down deep in the atmosphere, we expect there to be the atmosphere to be more homogenized. And as you go down deeper and deeper, this is going down into the deep atmosphere. Higher up, we expect very little homogenization. So the substellar point, that's kind of like high noon, that should approximately be the hottest part of the atmosphere. You have the west and the east terminator. One terminator is getting warm gas that's being advected to the night side. The other terminator has cold gas that's being brought around to the warm day side. And so only in a 3-dimensional model can you get a real feel for what's going on. And as I said today, one of the key aspects of this sort of work is now including clouds and how night side clouds, which might form on the cool night side, then get advected to the day side. And what you can produce from models like this are synthetic phase curves, synthetic spectra. A nice success is for WSP-43, a particular hot Jupiter. This is a phase curve of real data shown in black. These are 2 different 3D GCM models in red and in blue. You can see the general nice fit of the blue model, which is about 5 times solar, towards fitting some parts of the phase curve, although the night side of the model is actually warmer than that has been seen. But these are the sorts of observations that people are typically applying 3-dimensional models to compare to observations. So I wanted to switch gears now. We're about halfway through the talk, and so I wanted to switch from talking about atmospheres to interior structure models. There is, I would say, more emphasis lately on atmosphere modeling than interior structure modeling, but I know from a variety of other talks, you'll be hearing about other aspects of atmospheres. So I wanted to spend some time talking about interior structure. This could be compared a bit to Tristan Guillot's talk, who's talking about Jupiter's interior after the Juno mission. A lot of this work that I'll be talking about was done by Daniel Thorngren, who's currently the Trottier Fellow at the University of Montreal. And what Daniel was able to do was combine our understanding of planetary physics with a Bayesian framework to infer things about the population of hot Jupiters. So a key plot for hot Jupiter structure is looking at planetary radius versus the incident flux. This is like the solar constant. And what had been pointed out previously is below about 2 times 10 to the 8, there's a transition. This is about 1,000 degrees for equilibrium temperature. As you go to hotter and hotter planets, you see a dramatic increase in planetary radius. So Typically, the hottest of the hot Jupiters tend to have the largest radii. As you go to cooler hot Jupiters, you tend to eventually find a population that is no longer anomalously large. This black solid curve is the expectation for the radius of hot Jupiters from a model for kind of a 1 Jupiter mass, pure hydrogen helium planet. So if you're above this curve, there has to be some additional process which is causing the planet to not be able to contract over time. Whereas if you're below this curve, it likely just means you have additional metals in your planet that causes the planet's density to be higher. This figure is now about 5 years old, but it looks remarkably like this today. We'll see an updated version of it later. So what we want to do is try to assess the metallicity of hot Jupiters based on their radius. Of course, we can try to assess the metallicity of hot Jupiters based on spectra of their atmospheres, and we'll be doing that very soon. And we have some constraints already, but we can also do it based on a planet's bulk density. This is from a very simple sort of argument. If we have a model for a hot Jupiter's contraction over time, this is radius versus time for a given half Saturn mass planet. If it's made of pure hydrogen helium, we get a cooling track like this. If instead the planet has 30 Earth masses of metals inside it, or 60 Earth masses, or 90 Earth masses of metal inside it, what that means in terms of a model is that planet would have a smaller radius at any given age. And if we have a planet with a known mass, a known radius, and a known age, we can essentially look at if your model goes through that box. And if you go through that box, we can assess the amount of metals inside the planet. This is a very simple-minded way of looking at this with only 4 models. What we've done with Daniel Thorngren is looked at this in a fully Bayesian framework where we're looking at thousands of models, not just a sample of a few. And so our sample planets here are shown. For a given example, we can look at, let's say, WASP-8. So for WASP-8, we can make a plot of the amount of metals inside the planet and the probability. So we've done this for a sample of about 50 planets, not just a sample of a few. We have the mass of the planet, and we can assess the amount of metals inside the planet. What we don't actually know is if most of these metals are in a core, or most of the metals are instead in the envelope. But we can assess the metallicity of any individual planet by running thousands of evolutionary models. So instead of just running a few models, we can run thousands in a Bayesian framework to get an assessment of the amount of metals in any particular planet. And what we can create is a diagram like this. This is the inferred heavy element mass, the inferred amount of metals in the planet. And this is for a sample of, I think, 47 transiting hot Jupiters. We're going from around 1/10 of a Jupiter mass out to 10 Jupiter masses. And this is the amount of heavy elements in Earth masses. And what we see here is that there's a very good evidence that all hot Jupiters have at least something like 10 Earth masses of heavy elements. And as you go to higher and higher planet masses, you're getting an ever increasing amount of metals inside the planet. For comparison, Jupiter is here, Saturn is here. They fit in well amongst their cousin planets. And the key takeaway, I would say, of this diagram is that it's not enough to think about a hot Jupiter as having a 10 Earth mass core with a bunch of hydrogen helium piled on top of it. What we see is that the amount of metals scales as mass to the 1/2 power, and that giant planets are accreting lots of metals in addition as they accrete gas. We can find gas giants here that have accreted something like 100 Earth masses of metals. So we should expect all giant planets to be metal enriched compared to their parent star. We can look at another diagram, which is the metallicity ratio. This is Z of the planet. This is the metallicity of the planet compared to the metallicity of the star. The metallicity of the star comes from measuring its iron abundance, as one typically does for stars. The metallicity of the planet comes from our structure model that we just described. So the metallicity of this planet is coming not from a spectrum yet of the planet, it's coming just from our structure models. And again, we can make a plot that looks a lot like the solar system for hot Jupiters. So Jupiter on the whole is about 5 times solar if you include its core and its envelope. Saturn's about 20 times solar, if you include its core and its envelope. And we have a clear slope and spread for the hot Jupiters. As you go to lower mass giant planets, their metallicity increases. If all the giant planets had the same metallicity as their star, they would fall on this line here of around 1 down at the bottom. And clearly the trend shows that as you get to super Jupiters, but even these super Jupiters of several Jupiter masses, we expect to be enriched in metals compared to their parent star. So for the first time, what we found in this paper was this sort of universal relation for this mass metallicity diagram in terms of its slope and its spread. This is entirely complementary what people are trying to do in terms of atmosphere modeling. As we've talked about earlier, and the people are trying to devise if there's a mass metallicity trend for atmospheres. So on the left is a plot we already showed. On the right is a plot by Wellbanks et al. Based on retrievals, trying to assess the atmospheric metallicity as a function of planet mass by observing things like water vapor or alkali metals in hot Jupiter atmospheres. What we see, although there's a pretty clear trend in the bulk composition from the structure models, there is not yet a clear trend in atmospheric abundances from spectra. You can see the water vapor abundances don't really, it looks like it's consistent with flats. The alkali metal abundances are kind of all over the place. And the solar system trend for Uranus, Neptune, Saturn, and Jupiter is a very clear trend, but it's unclear if that's representative of hot Jupiters as well. So moving forward, as we get better and better spectra for atmospheres, we can make better mass metallicity diagrams on the right to see if trends exist at all. And that's complemented by what we're doing on the left from structure models. So this is a plot, of course, you've seen before, plots like it that show the planet mass as a function of orbital separation. We, of course, now know that the hot Jupiters are complemented by cooler giant planets, by super Earths and mini Neptunes. One of the things we can start to do is compare planet mass and stellar major axis with composition, right? So what we'd like to do for the hot Jupiter planets in the upper left of this diagram is not just know what their masses are and where they are, but understand their bulk composition from their density, which I just talked about, understanding their atmospheric abundances, which we talked about in the first half of the talk, and compare that to stellar abundances for a better appreciation of planet formation. And one of the things that is relatively recent when we combine the work of Thorngren with work from Johanna Teskey is that we can see that there's an interesting connection between stellar abundances and how it affects planetary metal enrichment. I'm just going to skip ahead here. One of the things that we see is we can measure the abundances of a wide range of atmospheric constituents. So in these parent stars, we can measure the oxygen abundance, carbon, iron, silicon, magnesium, and nickel. These are all the most important elements that form solids in hot Jupiters. And what we can see is if we measure all the solids, if we're measuring all the solids in the stars, this is Z star based on measuring those 6 elements, we can see that this trend exists still. The trend I showed before was based on just measuring the iron abundance. But what we can actually do is compare that to all the parent star abundances for this aggregate metallicity of the star compared to the planet from a structure model. We see this same slope and spread. But the most interesting thing we found, though, is that it seems like metal-rich stars don't necessarily make metal-rich planets. This is a plot of the residual metal. This is the excess metal that you might expect compared to the mass metallicity relation. If you're on the high side of this plot, then you're metal-rich compared to that mass metallicity relation. If you're on the low side of this plot, then you're metal-poor compared to that mass metallicity relation. And here, this is the metallicity of the parent star. If metal-rich stars made metal-rich planets with a 1-to-1 correlation, you'd expect to see a slope of 1. And that's not what we see. The slope is instead not that well measured, but the slope does not appear to be a slope of 1. So the interesting part is that although we know metal-rich stars more commonly make hot Jupiters. That's this plot on the bottom, right? That as you go to higher and higher stellar metallicity, the frequency of giant planets increases, and that's certainly true for hot Jupiters. The planets themselves don't seem to be any more metal-rich when they're around metal-rich parent stars. So it points to a complex connection between parent star metallicity, the disk metallicity, and the planet metallicity. So that's work that's published in Teskey et al. 2019. I'll skip this. So I want to come back to an enduring question for the hot Jupiters, and that is the question of inflated radii. And I showed a plot similar to this a few slides ago, where we look at the hottest of the hot Jupiters, and we tend to see planets that are the most inflated. Since the first detection of hot Jupiter transits in 2000, there's been this enduring question of what causes the inflated radii of hot Jupiters. And so we can see there's a cutoff at around 1,000 degrees, this dashed black curve. To the left of this diagram, there are no inflated gas giants. To the right of this curve, there's a very large population of inflated gas giants. We want to be able to assess why that is from the population. This is a fun plot I just threw up there for fun. You can study it at your leisure if you want to. This is a plot showing the wide range of explanations people have suggested as to why hot Jupiters have inflated radii. You shouldn't necessarily take all this in. I just want to point out that there's been a number of ideas postulated before in terms of tidal heating, in terms of new mechanisms that pump energy down into the deep atmosphere. And the basic idea is that we can use the population now to tell us what is probably happening inside the planets. So we want to turn the problem backwards. So a common idea for what causes hot Jupiter inflated radii is this idea that a small fraction of incident stellar energy is transmitted into the deep atmosphere. So there's a number of ideas for, if you imagine, so this is a pressure temperature profile of just a generic hot Jupiter. It turns out that all of the energy from the star is absorbed by about 1 bar. So if you imagine energy going into the planet from the star, all the star's energy is absorbed by about 1 bar, and then it's re-radiated back out into space. But it turns out if you could imagine a mechanism to transmit maybe 1% of that excess energy, if you could find a way to get about 1% of that star's energy down into the deep atmosphere, maybe to around 100 bars, that is enough to increase the entropy of the interior. So there's 4 different interior profiles here: red, black, black, red, blue, black, black, red. As the planet's interior cools off, the planet shrinks in radius. And so the yellow here is supposed to be a cartoon of some fraction of the parent star's energy getting transmitted into the deep atmosphere. And there's a variety of mechanisms suggesting how this might be possible. And so if you are able to do that, you can stall the contraction of a planet. And so let's say we have a given hot Jupiter that has a radius of around 1.6 Jupiter radii. That would be, let's say, over here where my cursor is. What we're typically blind to is how much energy you need to stall the contraction. Let's say, let's imagine we have a planet at 1.4 Jupiter radii, over here, 1.4. So a given simple model would have the planet contracting in black, and you would not be able to reach the planet's known radius if you have it at 1.4. But if you can transmit a small fraction of the parent star's energy into the deep atmosphere, you can stall the contraction and cooling. And that's what's shown in the gold and purple models over here. So what we want to do is we want to use the population to tell us if this is happening or not. And so we can look at this additional power and we can try to assess if it's constrained by the population or not. And so what we do is we put a Bayesian compositional prior on our planets. So from the previous work, we know the mass metallicity relation for hot Jupiter. This is now well determined. So for a given planet on the right-hand side of the diagram over here, this is about 250 planets. If we know from the mass metallicity relation how metal rich a given planet is and how much those metals are trying to shrink the planet, we can then better assess the amount of additional power in the planet, which is trying to increase the radius of the planet. And we can do this for all 250 planets on the right-hand side of the diagram, where we can assess the mass with an error bar. We can assess the planet's metallicity with an error bar. We know the system's age, and so we can assess whatever anomalous additional power we need to explain the radius. This is a diagram like this. So on the left-hand side, this is a parameter that we call epsilon. This is what fraction of the parent star's energy needs to get into the deep interior of the planet to stall the contraction. And people have suggested in the past that this number should be about 1%. And indeed, we find that this 1% number is pretty good. But in reality, it actually has an interesting functional form. If you had a 1% power number for all planets, what this would mean is that you wouldn't have enough energy at 1500 Kelvin. That would mean the planets wouldn't actually be large enough. But if you had this 1% number at very high temperatures, the planets would actually be too large. And so what we've found is that the shape is actually kind of like a Gaussian. This efficiency is about 2.5% for the hot Jupiters at around 1600 degrees. It falls off to very small values at cooler temperatures, which is in agreement with the population. We can see that below about 1000 degrees, we don't have anomalously inflated planets. This efficiency goes way down. The interesting aspect is that the hottest of the hot Jupiters also need to have this efficiency go down. And you can kind of see this from the population, in that as you go to the hottest of the hot Jupiters, what you're not seeing is a population of ultra inflated planets. They just don't exist. The most inflated hot Jupiters tend to be those at around 1600 degrees. And as you go to even hotter planets, the population tends to go to smaller radii. And that's where we get this downturn in the efficiency of converting stellar energy into anomalous power in the deep atmosphere. We can compare a model that has no inflation. And what this means is that we have all these positive radius anomalies where the planets are indeed much too large. If we include this Gaussian sort of shape, we can make this distribution look quite clean in terms of these are the cooler hot Jupiters, this is the hottest of the hot Jupiters. So this Gaussian yields this very nice fit in terms of radius anomaly versus this incident flux. And it turns out that, come on, where's the time? Okay. It turns out that this particular sort of Gaussian shape with a maximum around 1600 degrees is actually a prediction of one particular model for hot Jupiter inflation, and that's the ohmic dissipation model. This is a plot by Kristen Minot, 2012, and this is this epsilon parameter. This is the 1% number as a function of temperature, and indeed some models of ohmic dissipation predict a maximum around 1600 degrees. And so in the ohmic dissipation model, what you have is you have the planet has a dynamo generated field from the deep interior like Jupiter has. What you also have is a hot day side and a cold night side. And what happens is that on the hot day side, you ionize your alkali metals, and there's a flow from day to night. And that flow of ionized metals drives the current in the atmosphere, which drives a current deep into the atmosphere that's ohmically dissipated in the deep atmosphere. And it turns out that 1600 degrees is kind of a sweet spot, because below 1600 degrees, there's not enough ionization, thermal ionization, to ionize your alkali metals. But above 1600 degrees, the ionization is so strong that you tend to drag the flow, and so the flow becomes more sluggish. And so this sweet spot at around 1600 degrees is interesting, because it's a prediction of ohmic dissipation that matches what we see from the population itself. So I would say that if this isn't the answer, that ohmic dissipation isn't right, if it might be correct. If it isn't the answer, we at least now have a functional form that allows us to understand the intrinsic power for comparison with new theories. And there's a wide range of papers on the physics of ohmic dissipation. There's not yet agreements on how powerful ohmic dissipation might be, but this sort of curve is now telling us what the intrinsic additional power has to do as a function of planetary temperature. That it's weaker at cooler temperatures and it's weaker at higher temperatures, suggesting that there's some sort of drag on the atmospheric flow at the highest temperatures. I want to point out one more thing, checking on the time here. I just have a couple slides left. One of the things that I like to investigate is sometimes the atmosphere interior connection. And so it turns out that these anomalous interior energy sources can have an impact on what's happening in the atmosphere of the planet. So instead of looking at this epsilon number, we can think about how this additional power impacts the flux from the interior. The hotter the interior, the more flux comes out of the interior. So if you have a hot interior because you're a hot Jupiter, that means you have more flux coming out of the interior. You have a higher intrinsic temperature. So we can make a plot, instead of efficiency versus temperature, we can make a plot of the intrinsic temperature as a function of equilibrium temperature. And this peaks at around 1800 degrees. And so what this means is that hot Jupiters that are around this temperature have a lot of flux coming out of the interior, and that actually alters the temperature structure. So on the bottom here, I want to look at a couple different models. These are pressure temperature profiles from ultra hot Jupiters going to just generic hot Jupiters from right to left. It turns out that all these planets probably have much hotter deep atmospheres than were previously appreciated. And that's because these planets have very hot interiors. In yellow, for instance, this is a generic hot Jupiter of around 1300 degrees. If you expect the planet's interior to be about as hot as Jupiter, you would expect this radiative convective boundary to be down here at about 1000 degrees. If instead, for this particular 1300 degree planet, we read off that the T-int should be about 500 degrees, a model with a T-int of 500 degrees would be the solid yellow curve here that has a much hotter deep atmosphere. The upper atmosphere is the same in both cases, but if you have a hotter deep atmosphere, that makes you cross cloud condensation curves at a different place. These are condensation curves for various clouds. In the case of a cool deep atmosphere, you would form these clouds at 1000 bars and you would never see them. In the case of a hot deep atmosphere, you cross these condensation curves at around a bar and you would see these clouds. So it turns out that what the deep atmosphere and interior are doing can have important ramifications for allowing you to alter the temperature structure in the visible atmosphere. So what this might mean is that clouds should be more frequent in the atmospheres of planets than you might otherwise expect. So to conclude, I want to throw up some conclusions before we talk about some additional references. So I would say the full complexity of hot Jupiter atmosphere has not yet come into view. We've been doing a fantastic job with Spitzer and Hubble and other platforms to try to get spectra of hot Jupiters. I think in the era of new instrumentation for ground-based high-resolution spectra and for James Webb, I think what we'll see is that hot Jupiter atmospheres are even more complex than we've found already today. A hierarchy of forward and inverse models is necessary to understand these atmospheres. We need one-dimensional self-consistent models, three-dimensional self-consistent models, and inverse retrieval models. All three are essential to understand the physics and chemistry. And I think the interesting point we are now is trying to think about the interplay between those models. In terms of the structure of atmosphere of planets, we clearly have a mass metallicity relation for giant planets based on their structure, We're still trying to assess whether or not that mass-metallicity relation holds for their atmospheres or not. We're trying to assess some aspects of the planet-star composition connection, and do metal-rich stars make metal-rich planets? That's still not, I would say, clear-cut yet. For hot Jupiters, we now have some evidence that ohmic dissipation or a process like that may be the process that's leading to their inflated radii. And we can see that the connection between atmospheres and interior modeling have shown us that hot Jupiters have much shallower radiative convective boundaries than previously thought. And so the atmosphere-interior connection is important for those planets. In my last slide, I want to point out to some recent references that I think would be helpful if you want more information. There's two very recent nice references on atmospheres. One is by Madhu in 2019 in the annual review of astronomy and astrophysics on exoplanet atmospheres. Another is by Shizan in 2020 in research in astronomy and astrophysics. These are both very recent, important works that summarize all of our current understanding of exoplanets. And in some cases, Shizan also compares to brown dwarfs. And so hot Jupiters are a big part of both of these review articles. In terms of high spectral resolution, which is a field that's growing rapidly today, and I just didn't have a lot of time to touch on, there's two nice papers I would recommend. One is by Jane Birkbeam, 2018. This is a review of high resolution observations. There's another paper by Brogy and Line that's on comparing models to data. In terms of prospects for James Webb spectroscopy, James Webb will be launching later this year. There's a nice paper led by Tom Green that tries to assess how much more we'll know about hot Jupiter atmospheres in the era of James Webb compared to the previous era we're in today. And in terms of the structure of hot Jupiters, there's a nice review led by Isabel Baroff in 2014 that talks about the structure of giant planets generally. There's also a nice new paper by Tad Komacek that looks at modeling hot Jupiter evolution over time today with the MESA code. And so I recommend looking at all these papers if you want more information. There's a lot of great work by a lot of great scientists out there. And I'll be happy to answer any questions when we have our live meeting updates, I think in about 2 weeks. So thanks for listening, and I'll be interested in chatting more with you soon.